Hello and welcome back to Calculus 3, section 17.4 on Green's theorem. So this is going to have two components. So we'll start with the Green's theorem circulation form. So here is the theorem. Let C be a simple closed piecewise smooth curve. Let C Let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in a plane. So let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane. Assume that F, which is FG, where F and G have continuous first partial derivatives. Have continuous first partial derivatives in R. Then, and here we go, the line integral on a closed curve, which is why you have this circle on the integral sign. This is the first time you see this notation, all right? It's simply, this circle simply means all of these conditions on the curve C. All of this stuff that it's here, and here, and here, and here is encoded in this one circle around the integral. That's all it means for the notation. This is a good old integral. We are not learning a new integral. We are just learning a new notation because this curve C has the whole shopping list of requirements, as you can see, and it simply means that mess. So partial that is equal to, and then you can also write it in the exploded form, which is what we seen yesterday. And here is the $1 million part. You can write that as a double integral of g dx minus df dy dA. Technically, this equals that. That's the part that we are looking at. Now you are setting up a double integral over the region. You have a question? Subtraction, yes, minus. I'll make it. There we go. Subtraction, good. We are going from the vector field integral into calculating the area, but guys, this is the line integral, and over here you are looking into a single integral canceling with these, so it's still an area above, right? This one over here gives you a 2D, and this one over here gives you a 2D. Now, don't get confused that you're saying 1, 2, 3, so it's a 3D. No, because these are derivatives. So the derivative will cancel with one of the integrals, and it will leave a function behind, and then you have integral of a function, so it's a 2D. It's a 2D equals 2D. Your dimensions have to match. Now, the part that you are there, the parenthesis here, this is the second part of the same, and this is the definition part. So the definition here, this piece, dg dx minus df dy, is called the curl. Oh, hold on, move this away. I forgot to write the curl. So curl of f is equal to, so curl of f, so this over here is called the 2D curl, but I put that in a definition here. So curl of vector field f is given by this, and then we say if curl f equal 0, vector field is irrotational. Vector field f is irrotational. So if curl f is equal to 0, vector field f is irrotational. That's what it's. Now, how about we work out the problem from yesterday where we had curl applied to a radial field? We got a 0, right? So we had 0 on that one, and let's get the 0 now using the Green's theorem, and also check the irrotational field, because radial field is not rotational field, so it should be irrotational, right? So the curl should be 0. So let's go and check this. So if I have a radial field, xy, so if you're remembering, this is your f and g, and we were on unit circle, we parametricized full, so it doesn't cross itself. It's smooth, differentiable everywhere, no corners on a circle. Oriented counterclockwise, if you pick cosine first, obviously. Encloses a connected and simply connected region, which means the stuff inside the circle has no holes, and it's one piece. So the unit circle fulfills all of these criteria for us. And then f and g, which are just x and y, are both differentiable, and they have the first partial derivatives, right? They're continuous, which is 1 and 1. So we're all good there. So conditions, all conditions have been met for us to work out the Green's theorem. So what do I have? I have first to calculate curl of f, which is given as partial g, partial x, right, and so on. So partial g, partial x, this 0 minus 0 is equal to 0. So that's our curl of f, equal to 0. Immediately we see that xy is irrotational, because the curl is 0. But we can still calculate and show that it's 0. We calculated this in 17.2. Line integrals. There we go. Let's find it. So this is the flux, this is the second part. Here's the first part. This is where we define the line integral, and I said, okay, let's take a look at the circulation, the line integral in the vector field circulation form, and let's do it on a radial field. Here's a radial field. We did the radial field first. Here, a radial field. We did the whole procedure and came up with 0. Now, I'm using the same radial field, but through the Green's theorem, I have to get to 0. Well, we are already on a good start, right? Because the curl is 0. So now, when you set up your double integral over region R, which is the circle, you will be integrating 0 dA. And that's going to give you 0, obviously. Now, since you're integrating circle, you want to be in polar coordinates, so 0 to 1 and 0 to 2 pi, and you are integrating 0 times r dr d theta, and that's without going through all the hoops, is going to be 0 because you're integrating 0. There is no plus c because this is a definite integral, so this 0 is just going to kill everything off. Remember when we integrated in a previous section, 17.3, we integrated 0, we were getting constants. Well, those were not definite integrals. Those were indefinite integrals, and an indefinite integral has the antiderivative plus a constant, right? So look at the Green's theorem solution for this problem, right? We did not do parametrization, we did not do any of the calculation for r prime, we had no integrals to solve, we did nothing. Literally 0 work. We took 2 partial derivatives, and that was it. So when all of those conditions line up, you can easily solve this. So this was, again, a repeat of a problem from there. Now we can also repeat for this problem. Let's also repeat the radial one and get the same 2 pi answer for the rotational field, right? So rotational field, and that's f with the negative yx, right? So this is your f, this is your g, and if you find your partial derivatives, partial g, partial x minus partial f, partial y, that's your curl. Partial g, partial x is 1, minus, and then the other one is negative 1, so the whole thing is 2. We are again on unit circle. So now when I set up my double integral over region R, I am integrating 2 dA. The double integral is 0 to 2 pi, 0 to 1, and then I have 2r dr d theta because I am using a polar integral here because we are integrating circle. I don't want to deal with trig sub. That's too much. So when I integrate r, I get r squared over 2, and then 2 and 2 will cancel, so I just get r squared from 0 to 1. Oops. I just need one integral there because 1 is integrated. 0 to 1, I still have d theta. That's just going to be 1, so integral 0 to 2 pi of d theta is equal to 2 pi, which is the same answer we obviously got with the line integral. Green's theorem is a convenience for you to use if the problem satisfies the entire shopping list of conditions. Is the Green's theorem way to go all the time? Well, no, because if any of the conditions are not satisfied, Green's theorem doesn't hold, and it will give you most likely the wrong answer. In some situations, Green's theorem is the way to go because line integrals work only on the single line. And if you have a sharp corner or something, which is, remember, the piecewise smooth, if you have a sharp corner somewhere in 17.2, you have to do the separate line integral. So, if the problem is to solve some line integral of, I don't know, xz, you know what? I'm just going to say f dot t ds on a square. And that square is given to you, let's say, 3 and 3, like this. If this is a situation, well, you are calculating the area above this line, and above this line, and above this line. Guys, you have 4 separate areas here. So 17.2 needs to have 4 integrals. 1 for each side. 17.2 has to calculate, and then you add all of them. Then we add all of them. Line integral calculates the area of the curtain above the line C. If you are looking at the curtain at home, whatever the bottom of the curtain draws on the floor is the curve C. And the line integral gives you the area of the curtain because the top is cut off at z equals 10 or 8, whatever the height of your ceiling is. So let's say you have a curtain that goes all the way down touching the floor. So the line C on the floor is the line that is the input line for parametrization for your line integral in 17.2. So imagine now taking 4 curtains and arranging them into, perpendicular to each other, so they look like the walls of this classroom, but they're all curtains. Like you're going to do a magic trick. You walk in on one side, you walk on the other side, it comes out as elephant or whatever. So what you have there are 4 sides, and each one of those lines is going to have its own parametrization because the parametric lines, curves for all 4 lines on this square are different parametrization, which means that each one has to have its own integral, which is why 17.2 has 4 integrals, because it's a square. It would have 4 integrals if it's a rectangle, 3 integrals if it's a triangle, and it was a single integral because it's a circle, it's a one continuous line looping around, so cool. Circle had one integral there in 17.2. But guys, think about setting up a double area integral over a square. Hey, that's the cheapest integral you can have. Because in 17.4, the same problem has one integral which will have the double integral 0 to 3 and 0 to 3, and then over here is curl of f, and then you have your dx dy or dy dx. It doesn't matter which way you want because we said that they are interchangeable. This is the cheapest integral that you get, the very first whatever was 16.1, the rectangular double integral. So the Green's theorem holds for the square. The square is one piece, has no holes inside, it's closed curve around it, and it's a closed curve around it, and then it is piecewise smooth, which means that each one of the 4 lines has its own differentiable functions and all that kind of stuff. So it is a joke to solve this problem using Green's theorem, and then with the line integral, we'll just sit there for like an hour to compute 4 different integrals, because every time you have to restart the problem from scratch, because every time you get a different parametrization C, and with a different parametrization C, just look at 17.2, right? Parametrization for C gives you R gives you R prime is R and R prime is what's plugged into the problem to do the integral. So you have to do 4 separate problems here on 17.2. And they're all different, right? You don't get to recycle any part of it. You have to do everything from scratch all the way. Green's theorem, 1 problem. Green's theorem on a triangle that we had in a previous lecture when I had that triangle, again, you would have to do 3 separate 17.2 integrals, right? Green's theorem would take care of that with one single calculation. Now that would be 16.2 integral because it's the triangle in the region, but that's still much easier than dealing with the 3 separate line integrals. So what is the Green's theorem? Green's theorem is a convenience method for us to convert the line integral into the integral over the area using double integration. And it's really helping us save on time and calculation to do these things. And again, because you had the circulation and the flux form in 17.2, you are going to have for Green's theorem circulation and the flux form. So now all we need to take a look for the Green's theorem is the flux form of the Green's theorem. So flux form, and the flux form is going to have the same specifications on the region and the curve. So I'll just say same conditions as circulation. And we just get to write the formula for the flux form. So again, we are using the integral sign with the circle around it to indicate all of those conditions. This is the same integral you guys have seen, f dot n, normal vector, for the flux. Remember, the flux is the one that pushes out perpendicular, ds. And we have the notation. Remember, I told you I don't like this notation, but such is life, right? And here is the part that it's important. So now you are calculating the divergence. This part is called the divergence, dA over region R. And again, you are equaling your flux into your flux form line integral with the area integral on the other side. So coupled with this, the definition, the divergence of f is given by partial f partial x plus partial g partial y. And another definition, if divergence of the vector field f is equal to 0, we say that the vector field is source free. Then the vector field f is source free. So we learned yesterday that the flux will give you the value 2 pi on the radial field. So radial field is the one that shines the energy out, like the sun, and clearly sun is the source of energy, so the flux is going to have a value there because sun is the source, and it just spews these rays radially everywhere out, right, in 360 degrees in all possible directions around its sphere-like shape, right? So radially out everywhere, it shines out. Rotational field, however, right, has no source because the thing is just spinning. It doesn't give off energy out of it, it's just spinning in space. So we calculated with the line integral in 17.2 that the line integral in a flux form of the rotational field is 0. Now when you apply divergence to a rotational field, there is no divergence. The divergence is 0, and since divergence is 0, you guys are claiming that to be source-free. Divergence, you understand what divergence means, right? It just the two rays, right, will go away from each other forever, right? They don't bend back, they don't converge later or anything like that. So the sun's ray, right, the sun's ray that leaves the sun reaches the surface of the earth 8 minutes later, right? The sun is really far away, so it takes light 8 minutes to get here. If the sun is just to whoop, disappear, we wouldn't know anything for 8 minutes. It will be still daylight and so on. If you take a look at well, you can't do that anymore because of the white pollution, but if you are to go somewhere away from big cities and a lot of lights and so on, where the city lights and the highway lights and so on are not creating what we call the white pollution, which is the lighting up the sky. If you go far away from all of that and you look up in the sky, you will actually see the stars. From here in New Jersey, all you see are satellites and moon. So if you look at the sky and you look at the star, depends on how far the star is, that's how many years ago you get to see. So if a star is, let's say, 200 or 200,000 light years away, the light that you see is 200,000 years old. So you are looking at the past of that planet. So if there is a supernova that you are looking at right now, which is explosion of a star that was, let's say, 100,000 light years away, that means that star exploded 100,000 years ago. And you are seeing it now because that's how long it takes for the light to cover this insane distance that we can't even comprehend. Now, we are so pathetic, you can't get to Somerville over here when something happens on a highway, which is, 5 minutes away. Think about where is something that's 100,000 light years away. So, and that's, again, nothing on how far the galaxies are apart and so on. So it's just look up at that stuff. So we can use divergence to take a look at, we use the divergence to take a look at the divergence of the vector field. And if the divergence is 0, that means that the whole vector field is source-free. And then we can also use the Green's theorem, as you can see, to replace the flux. And that's the Green's theorem, guys. Bye.